So what we're looking at this week is we're looking at quadratic regressions, and then we're going to come back and look at some examples with logarithmic regressions, which is what we looked at last time. But I want to start off by talking about why quadratic regressions are useful. Quadratic regressions are useful, in my opinion, for two reasons. The first reason is why you would want to model anything using quadratics, which is that quadratics, as opposed to linear functions, has a turning point. So it allows you to model relationships which have turning points. In other words, relationships where it might be positive over some values of the x, and then it might transition to being negative over some values of the x, or the other way around. So for some values of the x, it's negative, and then for some values of the x, it is positive. Now, where might you see that? Interestingly, in many more places than you would actually expect. So one of the most common places where you see this sort of relationship is in the relationship between wages and age. Generally speaking, this is very common if you do sort of work with labor data to include age squared, because as you get older, and you're very young, and as you get older, you tend to start earning more, and then past a certain point, the older you get, the less you start earning. So it's positive at the start, and then it goes negative, right, for greater and greater values of age. Okay, so that's an example of a negative quadratic term. If you have a positive quadratic term, it actually goes the other way. You have something which goes down, all right, and then it starts going up again. Much more difficult to think of. An example of that. But an example of that would be something like how much time people spend on leisure. So if you model the amount of time that people spend on leisure as a function of age, when you're young, you spend a lot of time on leisure, as you guys are probably doing now in uni. And as you get older, the amount of time you spend on leisure goes down. As you start getting a job, you start getting busy. And then when you're old and retired, then of course the amount of time you spend on leisure then starts going up again. All right. So there are plenty of examples where these sorts of quadratic relationships are very useful in terms of modeling these phenomena. So what I'll do is let me have a look at the questions for this week, and we'll start off by having a look at the two data files that we're working with. Now, the first data file that we're working with is this shelf space data file, and in this data file we have two variables. The first variable is called boxes, and the second variable is called space. So these two variables here refer to the amount of, well, not these two variables, but these two variables broadly refer to a shop's decision to how much they should allocate to displaying a certain brand of detergent, and how much of that brand of detergent is eventually actually sold. So the reason why you might want to model this as a quadratic relationship is because of what this manager is saying, which is that sales would likely increase with more floor area. But once you increase floor area beyond a certain point, he actually suspects that sales are going to go down because people become suspicious when there's too much floor area devoted to a certain product. Okay? So the idea here is we're going to model it as quadratic, and we're going to see, well, does it have a turning point? All right? So what we're really doing here is we're really estimating this relationship right here. We're estimating the model boxes regressed against space and space squared. So let me jump over to R. I think I got a message. Give me a second here, and I'll try and bring that up. I have an R script of tutorial 4. I don't have it. I don't save my scripts, so so no, basically. All right, so let's jump back to here, and I'll import the data set and then show you how to run that regression. So the first thing we'll do is we'll import shelf space. So let's call that T8_1, and you should know how to import data files now. So I won't waste your time with that. And we can see that we have here two variables, boxes and space. And what we're going to do is we're going to run regression 1, which is linear model, and we're regressing boxes on space and space squared. Now, if you want to square a variable, you sort of do a square, but you have to do it inside this I here. What this I means is that anything inside the I is treated as a mathematical operation, all right? Data is equal to T8 underscore 1. There you go, you have the regression, and let's just summarize it and see what we get. Okay, good. So on first glance, it does appear as if the manager is correct because the coefficient of space squared here is negative and it's significant, all right? So remember that if you have, so let's say you have a general quadratic function, which is y is equal to ax squared plus bx plus c, right? Remember that if a is positive, then you have a minimum, okay? If a is negative, that means that you have a maximum, right? So I think you guys should be quite familiar with that idea, all right? And the other thing I want to mention as well is that the turning point, of course, will occur at x is equal to minus b over 2a. Okay, so I think that's something you might have learned a few years ago in high school. So you can use these points. They might sometimes be useful to just remember and keep in mind. Okay, so here you can see because the coefficient on the quadratic term is negative and statistically significant, the manager is actually correct. So it means that it's going to be going up and then it's going to hit a maximum and then start turning around and going back down, right? Okay, so it does support the manager's belief. Let's have a look at B3. And what I want to do in B3 is I want to have a look at how we calculate marginal effects and a look at exact and approximations. So the question here is basically that Melvin, there's a store in Melvin, has 20 centimeters of shelf space devoted to detergent, and it wants to estimate the change in the number of boxes sold if the shelf space increases by 1 centimeter in Melvin, so from 20 to 21, and then in Armadale, which would be from 35 to 36, all right? And of course, the changes will not be the same because of that non-linear relationship between space and boxes. So what I'll do here is I'll show you guys a nice trick, which is that if you have reg 1, if I do reg 1, $ coefficients, and in the square brackets, I just put 1, you see it actually returns me the first coefficient, which is the intercept term. 2 in here returns me the second coefficient, so on and so forth. All right. So what I'm going to do is I'm actually going to save the coefficients as B0, B1, and B2. And the reason I'm going to do that is it makes it much easier for me to do calculations later on if I could just use B0, B1, and B2 to refer to these three coefficients, right? And if you check these coefficients here against the output of the regression, you can see that they're the same, all right? So let's have a look at Melvin first. So let's have a look at what happens when we have space, what was it? 20? Okay. So if you want to calculate what is the amount of space, what number of boxes sold when space is equal to 20, that's beta 0 plus beta 1 times 20 plus beta 2 times 20 squared. And do the same thing for space is 21. And this will give you the exact change, right? So if Melvin were to go from 20 to 21, their marginal effect, as we call it, so this is the Melvin marginal effect, is space 21 minus space 20, which would be 16.45. All right, so that means that Melvin would sell 16.45 more boxes if it increased its floor space, displaying this detergent, from 20 centimeters to 21 centimeters. You could do the same thing for Armadale. So you have space at 35, which is beta 0 plus beta 1 times 35 plus beta 2 times 35 squared, and space at 36. And you can calculate the Armadale marginal effect as space 36 minus space 35. And what's this going to be? It's actually going to be negative. All right. And it's negative because Armadale is past the turning point. Yeah, going from 35 to 36 actually has a negative impact on the sales. It's actually going to sell 3.51 boxes less if it goes from 35 to 36 centimeters. In fact, you can find the turning point by doing the following. If you're interested in where it is, let's call it TP. It's going to occur at minus B over 2A. Okay, so B is the coefficient of the linear term, which is B1, and A is the coefficient of the quadratic term. So if you want the turning point will actually occur at 14 point, now that doesn't make too much sense. It occurs at 14. So why is this positive and this negative? That means that they should both be negative in that case, because this is 20. Turning point is, let me just check this briefly, minus B over 2A. That's interesting. But 14 doesn't make too much sense either, because 43 divided by what, 1.2, how does that get us to 14? Because if I were to do this, divided by, I'll take the negative out, so it cancels the negative on top. Whoops, 2 times this. Yeah, that makes much more sense, because then Malvern at 20 is below the turning point and Armadale is above the turning point. So, and beta 1, let me just check, is 43. I know what I did. Do you guys know what I did? I know what I did. Can you guys see it? That's what I did. Brackets, exactly. Okay. 32.86. There you go. So you can see here that the turning point occurs at about 33. So that explains why Malvern, which is below the turning point at 20, has positive impact, but Armadale, which is above the turning point at 35, has a negative impact. So this is how you calculate it exactly. Of course, an alternative way that you could have done this is by using an approximation. You can use an approximation using the first derivative. And for small changes, that approximation will be quite close. 1 centimeter here in this case is actually quite large. It's 5% change. So it won't be quite the same, but with really small changes, you could actually use the derivative. So the derivative is just doing an approximate change by doing a linear approximation as opposed to an exact change, okay? So remember that if you have y is equal to ax squared plus bx plus c, right, then your derivative, which is dy dx, is equal to 2ax plus b, all right? So that gives you the instantaneous gradient at any point. You've probably seen this in high school as well, so I won't need to explain what a derivative is. But in this case here, your derivative is actually given by, so d boxes, d space is actually given by beta 1 plus 2 beta 2 times space, okay? So if you wanted to find the approximate change for Malvern, so Malvern ME approx, let's say, what you would do is you would do beta 1 plus 2 times beta 2 times 20, okay? And you can see that they're fairly close, right? 16.5, 17.1, yeah? So this would be the approximate change if you were using the derivative to approximate it. And Armadale, marginal effect, approx would be beta 1 plus 2 times beta 2 times, what's Armadale? 35. Okay, so with Armadale, you can see that it's, Negative 3.51 is the exact change, and the derivative approximation will give you negative 2.85, right? So again, it's close, but it's an approximation. It's a linear approximation. Okay, so that's using this derivative here. All right. Find and interpret this coefficient beta 1 hat plus 50 beta 2 hat. Okay, what is this? So what is 50, oops, no, not 50, beta 1 hat plus 50 times beta 2 hat? So you can see here that if we compare this to the derivative, we can see that this is actually the d boxes d space evaluated at space is equal to 25, right? So if you look at this expression here and you compare it to this, right, you have beta 1, you have beta 2 here, so therefore 50 must be 2 times space, right? So space is equal to 25. So it's the derivative evaluated at space is equal to 25. If you actually want to evaluate it, then it's 10.46, right? So it's basically telling you that for a space of 25, increasing your floor area by 1, you'll sell about 10.46, approximately 10.46 boxes more. Okay, so the reason why we're doing this is that you can actually perform hypothesis tests based on this, okay? And what we're trying to do here is we're trying to run this test, and I'll talk about the test we're trying to run, and then I'll come back around to how we actually come to the results we need in order to run this test. What we're trying to do is we're trying to test the following. We're trying to test beta 1 plus 50 beta 2 is equal to 15 against the alternative. Beta 1 plus 50 times beta 2 is not equal to 15. Right? What I'll usually do is I actually usually put this on this left-hand side and just have this equal 0. Okay? And the reason I do that is it's just easier to have everything on the left-hand side, because when you do the test statistic, so this test, which is t-stat, on the left-hand side, beta 1 plus 50 times beta 2 minus 15, right? So the numerator of the t-stat is just the left-hand side if your right-hand side is equal to 0, okay? And you divide by the standard error of beta 1 plus 50 times beta 2. You don't need to have the minus 15 because constant shifts are not going to change the standard error. Okay, so you don't have to have the 15 in there. Now, obviously, this numerator is really easy to figure out, right? If you want to figure out what it is, there you go. Okay, that's what the numerator will evaluate to, of course. But what about this denominator, this standard error? That's a little bit harder, yeah? So you actually have to put in a bit of work to try and calculate what this standard error is. And this standard error, so let me write this out here. Beta 1 plus 50 times beta 2, that's equal to the square root of the variance of this quantity. Okay, but what is the variance and why does that help us? Well, we can actually use an identity here that might help, which is that the variance of A plus B, actually two things. Okay, the first, variance of A plus B is equal to variance of A plus variance of B plus 2 times the covariance of A and B. Okay, whoops. That's the first thing that you need to remember. Two other things that might be useful, which is that if you have the variance of AX, where A is a constant, that's A squared times the variance of X. And the third thing that might be useful is that if you have the covariance of, let's say, AX and BY, that's AB times the covariance of XY. So basically taking things out of the variance, you need to square them. Taking things out of the covariance, you do not need to square them, okay? Because they only affect one term. Okay, so in other words, the variance of beta 1 plus 50 times beta 2 is going to equal variance of beta 1, okay, plus variance of beta 2, but you have to take the 50 out front and square it. It becomes 2,500 times the variance of beta 2, times the variance of beta 2, plus 2 times. Now you take the 50 out front, that becomes 100 times the covariance of beta 1, beta 2. Yeah, so that 100 is from 2 covariance AB, but you take the 50 out front, so you have to multiply that by 50. All right. Okay, so as long as you can find the variance of beta 1, variance of beta 2, and the covariance of beta 1 and beta 2, can find the standard error. Okay, so how do we do that? Well, VCOV is a function that allows you to find the variance covariance matrix of a certain series of regressors. So if I do VCOV reg1, what it'll output here is it'll output the variance covariance matrix of the coefficients of regression 1. Now on the diagonals, you have the variances, and anywhere that is not on the diagonal, you will have covariances. For example, if you want the variance of beta 1, which is space, that will be 130. Okay? So you can actually even type here, var b1 is equal to vcov reg1, and what element is it? It's element 22. Yeah, so this is element 22 right here. What about variance of b2? What element is that? Well, that's in the bottom right here because that's space squared, right? So that's the variance, it's element 33. And lastly, the covariance of b1, b2 is the element. You can either get the element from here, okay, so space squared and space. So that's element 3, 2. Or you can get it from here, which is element 2, 3. Yeah, both the numbers are the same because the matrix is symmetrical, okay? So you can either do 2, 3 or 3, 2, and both are fine. Okay, so what this will do here is it'll extract out the elements from inside this variance covariance matrix and then store them into these variables here. And what that allow you to do is that allow you to calculate the standard error. So the standard error, I'll just use SE, is going to be the square root of this variance here, which is the variance of B1 plus 2,500 times the variance of B2 plus 100 times the covariance of beta 1 and beta 2. Okay, so you have your standard error, finally. What's the standard error? 2.732818. All right, so now you can calculate your t statistic. T is equal to this quantity here, numerator, divided by your standard error that you've just calculated, right? So what's t? That's your t statistic, okay? You're going well so far. All right. So what would you do here? How would you perform the test? Well, you calculate the p-value, all right? Now, this is a two-sided test. How do you calculate the p-value for a two-sided test? Manually. How do you do that manually? The first thing is you need to realize which side of the distribution you're coming in from. Are you coming in from the left or are you coming in from the right? Okay, so here, I'll give you the basic gist of it. If the test statistic is negative, that means you come in from the lower tail. Okay, if the test statistic is positive, you come in from upper tail. This has no bearing on your actual accept-reject decision because it's a two-sided test. But you need to get this right because when you specify, you need to tell the function whether you're coming in from the left tail or whether you're coming in from the right tail. In this case here, you're coming in from the left tail because it's a negative number. All right. Then you have to multiply the p-value by 2 because it's a two-sided test. Okay. So PT. Okay. Let's put in t as our input, comma. Degrees of freedom will be 22. So 25 minus 2 minus 1. You could just check the regression output as well. It'll tell you right here, 22 degrees of freedom. All right. So 22. And then here you have to say lower tail is equal to true or false. In this case here, like I said, because this is negative, you're coming in from the lower tail. So lower tail is equal to true, okay? Because you're coming in from the left, right? If t is less than 0, you come in from the left. This has to be true. And you multiply by 2, okay? Because it's a two-sided test. So this is your two-sided p-value, 0.1109. Okay? So, you do not reject the null, as p is not less than 0.05. Okay, that's your conclusion. All right, now that's how you do it manually. How do you do it using R? Well, you need the package AER. So if you haven't installed the package, I won't run this command, but if you haven't installed the package, this is what you need to do. Whoops, I'll comment this just so I won't actually reinstall my AER package. That's what you would do, right? Install the package as AER, and that'll install the AER package. Once you've done that, just load up the package with library AER and do the following: linear hypothesis. And then in the first thing, you put your regression model, which is reg1, comma, and then in quotes, you put in your hypothesis using these names here as the names of your parameters. Okay, so here it is. Remember what it is? Beta 1 plus 50 times beta 2, right? So beta 1 is space. Beta 1 plus 50 times beta 2 is this quantity here. Minus 15 is equal to 0. All right? That's how you would enter it into R. Okay. That'll give you the output to your hypothesis test. What you want to do is you always want to make sure that your hypothesis up here is correct. So space, which is beta 1 plus 50 times beta 2 is equal to 15, which is, of course, the test that you're trying to perform. All right. Look at the p-value, 0.1109. Look at the p-value we calculated before, 0.1109. Okay, so both the manual test and the test using R are giving us the same result. Okay, so you can conclude here that you don't reject H0 as P is not less than 0.05. Okay. Now, you might notice here, and I'll mention this briefly, that this doesn't give you a T statistic, but actually gives you an F statistic. Why is that? Because it allows you to test multiple hypotheses. I won't get this into this right now, but the F test is used for multiple hypotheses. For a single hypothesis, this number is just the square of the T statistic. Okay, so if you take the T statistic here and you square it, or just do this, T squared, right? You can see that 2.7583 is the square of the T statistic. Okay, so it reports the square of the T statistic as opposed to the T statistic. Why it does that? I'm not going to get into why it does, but for just one hypothesis, that might be useful to know. Okay. All right. So I think that's it. Let's move along. Before we do that, any questions? Thumbs up, thumbs down. Does this all make sense? We all good? Yep. Okay. If you have any questions, let me know. Otherwise, I'll move swiftly along to having a look at this second model here. And in the second model, we're actually going to be looking at the relationship between some prices of some art pieces and some characteristics of those art pieces. So there's a bit of an introduction at the start of the file to what this data set is all about. But by and large, it's just some art auctions, some paintings, I believe. Price represents how much those paintings sold for at an auction. Age is self-explanatory. It's age of the painting. Area is the size of the painting in tens of square inches. That's important to remember. That the units is actually not square inches, but the units in area is tens of square inches. Okay. Area squared is self-explanatory. Signed is whether it was signed by the artist. So this is a binary or dummy variable, 1 or 0. And DREC is whether the sale occurred during a recession. And this is also a 1 or 0. Okay, so let's try and estimate this equation here. And we'll try and interpret the coefficient estimates for age, signed, and DREC. Okay? Okay, so let me draw a line. Okay. And what I'm going to do here is I'm going to import this data set, which I've got here as art.csv. Okay, t_2 is read.csv, art.csv. Okay. So here's the data set, and let's run the regression. So reg2 is LM. Now it's a log of price. So I, and then in the brackets, ln price, tilde. And what are the variables? Age, area, area squared, age, area, area squared, signed, and derec. L n, this should be log, sorry. Price, data is equal to T8 underscore 2. I'm making a lot of mistakes, but I managed to get there. Okay, so summary reg2. So here we can see that we have all of our different coefficients. Now, you might notice this sort of scientific notation here. If you understand scientific notation, all this means is, now 2.541 times 10 to the negative 2. So just think of this E as times 10 to the power of. If you don't understand scientific notation, you've never seen it before, it just tells you what to do with the decimal place, okay? If you have a negative number, you move the decimal place to the left that many places. If you have a positive number, you move the decimal place to the right that many places. In general, for numbers that are big or numbers that are small, you should always use scientific notation. Why? Because if I asked you, what is this? How do you tell me? Well, you've got to sit there and say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and count the number of zeros, right? Can you tell the difference between this and this very easily? No, right? You can't tell the difference between these two things very easily. But, and this is much more easy to tell the difference between, okay? So if you're ever writing numbers like this, please do not write numbers like that, okay? Write numbers like this, yeah? Or, or if you're writing by hand, 5 times 10 to the negative 10 or whatever, right? If you have 10 decimal places to the left, okay? Because when you're reading, you can't tell whether it's this or this very easily. That's a problem. Okay, so that's scientific notation. Generally, when you're working with really big or really small numbers, scientific notation is really useful because rather than using a linear scale, it switches it to using an exponential scale. So it allows you to represent really big numbers and really small numbers using much less space, okay? Alrighty, so let's interpret these coefficients here. So coefficient on age, if a painting is 1 year older, on average, price is, what would you say this is? You have to multiply it by 100 because it's a percentage. Remember, it's been logged, so 2.54% higher. Keeping the other variables constant. So what are the other variables? Area. Whoops. Keeping area. Signed. Derec constant. You always have to make sure that you specify that you're keeping the other variables constant. Right? If you don't specify that, it's actually incorrect. So if a painting is a year older, its sale price is about 2.54% higher. Okay, what about signed? If a painting is signed, on average, price is, what is that? 63.07% higher. Is that right? Yeah. Keeping. Area. Age. Derec. Constant. Okay. Now, something to note is that the effect of signed is actually statistically insignificant. Derec is that if a painting is sold during a recession, on average, price is 77.76% lower, keeping, etc. constant, right? You get the point at this stage, okay? All right, so, only thing I would mention here is that you have to multiply this by 100 and it becomes percentage because the variable that's been logged changes in percent. Remember I told you that last week? Yeah. So that's one way that I remember how to interpret log regressions. Other important point here that I would mention as well, just briefly, is to always be careful of the sign, right? Higher or lower. I marked some exams a few semesters ago, and it's actually pretty common to get this mixed up. You'd be surprised at how many exams just mix up lower and higher, and don't match it up with the sign. So you want to make sure that that's something that you're paying attention to. Other thing I'll note here, it's beyond the scope of the question, but also note, just for interest's sake, that the relationship with area is initially positive, but then goes negative. How do I know that? Because the coefficient of area squared is negative, meaning that it's sort of a hump-shaped parabola, right? So it goes up and then goes down, okay? So it's something you can notice pretty quickly when you're looking at the output here. Okay. Find and interpret this quantity here, beta 2 hat plus 50 beta 3 hat. Okay. What is beta 2 and beta 3? Oh, that has to do with area. Okay. So here, let me just say that d price, d area, is equal to beta 2 plus beta 3, 2 times beta 3 times area. Okay. So if you're asking what is beta 2 plus 50 beta 3, it's the same as the answer that we gave before, which is that it is the marginal effect of area. So this is similar to what we did in the last question. So just comparing the two, you can see that this is the marginal effect of area evaluated at area is equal to 25, which is actually 250 square inches because area is measured in tens of square inches, right? That's all that is. Okay, 95% interval for beta 4. Conf int. Okay, reg 2 parameter is, what's beta 4? Beta 4 is signed. So you put in here, brackets, in quotes, signed. And then you put what probability you want. So you want a 95%. So you put 0.95 here. Okay, and you get the confidence interval for signed. What does it tell you? Well, you can see that the 95% confidence interval. So first of all, let's actually interpret the interval. We are 95% sure that a painting that is signed can decrease value by, or price by 13.65% to increase price by 139.8%. Okay. Which is a really, really wide interval. Yeah, so note that it's a really wide interval, which just means that it's that the certainty of the effect is very low. Okay, but the most important thing I would actually note here is you note that the interval contains 0, right? Which implies that we are not more than 95% sure that the effective sign is not 0. Okay, so therefore, the effective sign is insignificant at 5%, because for it to be significant at 5%, what you're really saying is that you need to be more than 95% sure it's not 0, but 0 is in the interval. Yeah, so you can't be more than 95% sure that it's not 0 if 0 is in your 95% interval, because you're saying you're 95% sure that it's in this particular interval, and in that interval, 0 is there. So 0 is not outside of that 95% interval. So that's why it's insignificant. And if you look here, it's fairly obvious that it's insignificant because the p-value is not less than 0.05. Okay. All right. So that's how you get the confidence interval, conf int. Okay. How much more valuable are large paintings? Using a 5% significance level, test the null hypothesis that painting an extra 10 square inches, which is area is equal to 1, not 10, because remember that area is tens of square inches. increases the value by 2% against the alternative that increases the value by more than 2%, and you do it at 250 and 900. Okay, so what you're really doing here is you're doing the test. You're doing this test, okay? You're testing H0, the derivative, which is beta 2 plus 2 times beta 3 times area, is equal to 2%, which is 0.02, against the alternative that it is greater than 2%. Okay? Greater than 2%. All right. And you're going to perform the test at 250 and at 900. So you perform the test at area is equal to 25 and perform at area is equal to 90. Okay? All right. Now, I need to be really clear about something, which is that the linear hypothesis command, sorry, phone buzzed. The linear hypothesis command only works with two-sided tests because, like I said before, when it gives you any output, let me just write it down and you'll see exactly what I mean. Okay, reg 2, let me just do this at 25 real quick and you'll see what happens. So this will be area plus 25 times 2 is 50 times I area squared minus 0.02 is equal to 0. You'll see here that the statistic that's given is an F statistic, which means that regardless of whether this T statistic, which is used to construct the F statistic, remember F is equal to T squared, regardless of whether T is positive or negative, F is always positive because F is equal to T squared. F cannot be negative, all right? So you have to be really careful. And if you want to do a two-sided test, you actually have to do it in 2 steps. Step 1 is to evaluate the hypothesis and check its sign. Okay? You only reject. Now, the sign needs to be correct. So the same as the alternative to ever reject. So what that means is that if the sign is incorrect, then you cannot reject the null, regardless of what the p-value is, because it's on the wrong side of the distribution. Okay? So if the sign is incorrect, there is no rejection. Okay? So I'll actually write that down here in caps because this is important. If the sign is incorrect, i.e. not the same as H1 sign, okay? That means you never reject H0 because it's on the wrong side, okay? It's on the wrong side of the distribution. So it needs to be correct, okay? And then step 2 is to check p-value divided by 2. And the p-value here is the p-value given by linear hypothesis. Is less than 0.05, I meant to say. And this is the one that's given by linear hypothesis, right? Okay, so let's see how we would evaluate this at 25. Step 1 here. Okay, so test at area is equal to 25. Okay, so step 1 is you have to evaluate this quantity right here. Okay, so let me extract out. Let me just extract out the beta 2 and beta 3 real quick. So beta. Okay, I've already used beta 2 before. It's fine. I'll just override it. Is reg 2 coefficients. Do some counting. 1, 2, 3. And beta 3 is coefficient 4. Okay. Whoops. I forgot the last. I didn't close that square brackets. Okay, so the step 1 is you actually have to evaluate what is beta 2 plus 2 times beta 3 times 25. Okay, and this is indeed positive. All right, so step 1 is positive, which is a pass. Okay, so then you go on to step 2 because there could be a rejection. All right, so step 2 is then you perform this linear hypothesis test. okay? And as you can see, if you perform this linear hypothesis test, the p-value is indeed less than 0.05, okay? So because the p-value is less than 0.05, you will reject the null at 5%, okay? Now, if you were to do the test that area is equal to 90, let me show you how that works. Okay, so if you were to do this, then again, you have to do step 1 and step 2. So let me do this here. Step 1, so I won't know the result yet, so let me delete this result here. Step 1 is rather than having 25 here, this will be 90. And then again in step 2, rather than having 50 here, this will be 180. So again, I have to look at this quantity here first. And again, this is positive, so that's a pass, right? So if this was negative, that would be a fail straight away, okay? This is positive, so it's a pass, which means that it could be a rejection, but it depends on the p-value. If this is negative, it will never be a rejection, regardless of what the p-value is, because sure, if you have a small p-value, you are certain, but you're certain of it being in the wrong direction, okay? All right, let me give you an example of why this is the case. Actually, let me just do this and then I'll talk. Okay, p-value divided by 2 is not less than 0.05. Okay. This should be p-value divided by 2, my bad. P-value divided by 2 is not less than 0.05, so therefore no reject. Do not reject. H0 at 5%. Okay, let me just talk about why this makes sense. What does a p-value tell you? What does the p-value tell you? P-value tells you how sure you are of something, okay? So let's say you're talking about someone's height, all right? And you say, I don't know, Alex, I don't know how tall you are, but let's just say I make a claim. Alex is a really, really tall guy, okay? And then I go to someone who's actually met Alex in real life and can tell me how tall he is, and he tells me, oh, you know, Paul, I'm really, really certain about Alex's height. That's just a p-value. You see that it actually can't conclude whether my statement is true or not. Yeah, because that p-value does not tell me anything about the sign, right? Is Alex really, really tall? Is he really, really sure that Alex is really, really tall? Or is he really, really sure that Alex is actually really, really short? Yeah. So that's all that the p-value tells you. It simply tells you how sure you are about something, okay? It doesn't tell you about the direction in which you are sure. That's why you have to evaluate the direction first. If you are really, really sure, but you're really, really sure in the opposite direction, well, of course, that's actually not evidence for rejecting the null. It's actually evidence for not rejecting the null, okay? So in that case, that's why if the sign is already incorrect, you would never reject the null, all right? It's very important that you remember that when you're using linear hypothesis, because it's actually an F-test. That being said, I'll sort of make the more broader point, which is that usually people don't do one-sided tests. I very rarely, if ever, do one-sided tests. So that's also another thing as well, which is probably why the standard is to use F-tests here, because most people don't do one-sided tests. So whether that's actually a big issue or not, I'm not too sure, but practically I've never felt the need to do a one-sided test. Okay. Any questions, let me know. Otherwise, enjoy your weekend, and I'll see you guys again next week. Which part of the lecture or tutorial do you think will be helpful for assignment 2? Oh, I don't know. It's about regression. So it's certainly the past couple of lectures and tutorials, the ones on regressions. I would specifically review any material that we've covered on dummy variables. So that will be last week. I remember I talked about dummy variables either in Wednesday last week or Friday last week. One of the two would probably be quite useful. Aside from that, I think that that regressions, especially anything to do with dummies, is probably what you would want to review if you're stuck on anything with assignment 2. Okay. Sure.